This is the second example of the application of the work-energy theorem to problem solving. So let's take a look. A 15 kilogram box sits atop a 3-meter icy hill. So here's that box that we can assume the hill is frictionless. And then a little man does 600 joules of work. Here's that little man on the box to get it moving so that it slides down the hill. So it's eventually going to end up down here at the bottom of the hill. At the bottom of the hill, it undergoes an inelastic collision with a 9 kilogram box. So eventually that box slides here and it hits it. And then the two boxes slide 8 meters across a concrete sidewalk, concrete slab, and eventually come to rest. So here at the end, the two boxes now have this final velocity of 0 meters per second. Okay, so there's a lot going on here. We've got the box going down the hill, colliding with the other box, sliding across the high friction concrete. Okay, so let's take a look at how we can use conservation of energy and conservation of momentum along with the work-energy theorem to figure out what's going on in this problem. So part A, it says use the bar chart below to diagram the work-energy relationship for the 15 kilogram box as it slides down the hill. The initial state is at rest at the top of the hill. The final state is just before colliding with the 9 kilogram box. Okay, so let me clean up this diagram a little bit. So we're talking about just this part here at the top. This is the initial state. And the final state is here just before it collides with the 9 kilogram box. Then determine the velocity of the 15 kilogram box at the bottom of the hill just before the collision. Okay, so we know initially the velocity is 0, and the final velocity, though, is the unknown. So that's what we're trying to figure out in this problem. What is that final velocity just before it hits the other box? All right, so using this conceptual diagram, a work-energy bar chart, how is the energy in the work sort of moving in this situation? Well, up here at the top, the box is initially at rest, so it has no kinetic energy, okay? But it has this 3 meters worth of height, so it does have some potential energy. So I'm going to give it some amount of potential energy, okay? I'm just making up 3 bars. And then we're told that, here it is, right? A little man does 600 joules of work on the box to get it moving. So that means there's going to be some amount of positive work done. Okay, I'm just using 2 bars. I could have done 1 bar. And then what happens is down here in the final state, the energies are now transformed. Okay, at the bottom of the hill there is no height, so there's no potential energy. So I'm going to draw the potential energy at 0. But it will gain speed, right? It's going to accelerate as it goes down this hill. And so if I look over here on the left side, I see that I have 5 total bars of energy, which is the potential energy plus the work. And so here I'd better have 5 total bars. Now, if there's no potential energy, then that must be 100% kinetic. So I'm going to fill that up, okay? So that is conceptually what's going on, right? We've got this potential energy at the top of the hill. Then it's gaining some energy because of the work that the man is doing and pushing on that box. And then down at the bottom of the hill, all of that energy is being transformed into kinetic energy just before it hits the other one. Okay, now that we have this, we can actually figure out this final velocity here at the bottom. And so we're going to use the work-energy equation to do that. So as a reminder, the kinetic and the potential initially, I'm going to add the subscript I, plus any work that was done to that box is going to be equal to the kinetic and the potential in the final moment, okay? Well, initially the kinetic is 0. The potential is going to be made up of mgh, and then the work from the little man will be equal to the kinetic energy in the final state. That's 1/2 mv squared, plus the potential energy in the final state, which is down at the bottom of the hill, is nothing, okay? So I can go ahead and plug in my numbers. I've got 15 kilograms times 9.8 meters per second squared. starting at a height of 3 meters, plus the work done by the little man, which we're told is 600 joules, will be equal to half the mass, 15 kilograms, times the velocity squared. I'm going to call that V final. Okay? All right, so multiplying on the left side, adding the 600 joules, solving for V final, I get that the final velocity just before hitting the other box is 11.78 meters per second. Okay, so I can add that to my picture here if I want. 11.78 meters per second. Okay, let's keep going. Next, determine the velocity of both boxes just after the collision. Okay, now if you haven't studied the conservation of momentum yet, this is going to feel a little bit confusing. But if you have studied the conservation of momentum, then here's the idea. The product of mass and velocity of the first box plus the product of mass and velocity of the second box before the collision, so I'm going to call that like in the initial moment, will be equal to the product of the mass and the velocity of both boxes after the collision. Now, after they collide, they stick together and they become one mass. So we write that like this. The mass of the first box plus the mass of the second box is their combined mass, and they're going to have this like common velocity after the collision. I'm going to call that V final. Okay? This is conservation of momentum for an inelastic collision. So here we go. The first box, and by the way, I'm defining these this way. I'm going to call this I'll call this box 1. This is box 2. Okay? And then when they stick together and they slide across the sidewalk, right? This is box 1 and box 2 together as a combined object. All right, so plugging in the numbers, the first box is 15 kilograms, but it is at rest, right? And the second box is 9 kilograms, but it is also at rest. So there's no momentum. Oh, I'm sorry. This is, the initial moment is just before the collision. My bad. So this number here is not 0, right? The 15 kilogram box is actually going this fast, 11.78 meters per second, just before the collision, right? It comes in, it hits the 9 kilogram box, which is at rest, and then they move together, okay? After they stick together, their combined mass is 15 plus 9, and they move together with a common velocity, V final. Okay, so we can see that this part goes away because the second box has no initial momentum. And so solving for that final velocity, 7.36 meters per second. This is at the end of the sidewalk, right? So over here, this velocity now at this moment is 7.36 meters per second. That's for both boxes because they're moving together. And I'm going to slide this description just to the left a little bit because that's just true for this box here. All right, finishing this up. Now, it says use the bar chart to diagram the work-energy relationship for both boxes as they slide across the concrete after their collision with each other. Be sure to carefully define the initial and final states for the boxes, then determine the coefficient of kinetic friction between the boxes and the concrete. Now, we need to grab another piece of information that we might have overlooked before, which is this, that the two boxes slide 8 meters across the concrete slab, okay? So as I move from this collision moment to then here, when they slide across, they're going to be sliding a distance of 8 meters. It's an 8-meter slide, okay? So I know that their initial velocity, here I'm gonna call this V initial, right? They're going to come in at 11.78 meters per second. And then their final velocity is the 7.36, and this happens over 8 meters. So let's try that, right? Okay, so conceptually, what's going on here? So right after the collision, the two boxes are going to have all this kinetic energy, okay? But they're going to have no potential energy because they're flat on the ground. They're both touching this concrete slab. They have no height, okay? And then all that kinetic energy is eventually going to come to zero because the two boxes will come to rest, right? V final is 0. And then the boxes are sliding along a level path the entire time, so the potential energy in the final state is still 0. So again, this initial state is I will say at the beginning of the concrete slab. And the final state, I will say at the end of the slab. I'll say at rest, at end of concrete slab. Okay. Now, you'll notice that there's an imbalance here because on the left side, I've got 5 bars of energy, but on the right side, I have no bars of energy. So I've got a problem, okay? And this is how I can solve it. I need to add some negative work here. This is work that's done by friction on that concrete slab. Now, if I add these up, the total number of bars on the left is the positive 5 plus negative 5, so that's a total of 0. And then that will now agree with the total of 0 bars on the right side, which is describing the amount of energy once the two boxes come to rest at the end of that concrete slab. Okay, so let's do the math and finish this up. So as always, the potential plus the kinetic in the initial state plus any work that's done will be equal to the potential plus the kinetic in the final states. Okay, so at the beginning of the concrete slab, the boxes have no potential energy, but they do have some kinetic energy related to their initial velocity. And then there's going to be some work done by friction. So that work is specifically the force of friction times the distance. Then I'm going to set that equal to the potential energy in the final state, which is also 0, plus the kinetic energy in the final state, 0 because they come to rest. Okay? All right. So I can say that and we're missing this coefficient of kinetic friction statement, right? So that's actually going to come in right here. So let me draw one more expression to see how this involves the coefficient of kinetic friction. So we can say that 1/2 mv initial squared plus, so force of friction is always mu sub k times the normal force. Times distance is going to be equal to 0. Okay, and then let me break that apart even more. The normal force for an object that's just sitting on a flat surface is its mass times gravity. So let's break that down one more step. Mu sub k times mg is the normal force times the distance is going to be equal to 0. All right, plugging in the numbers. So I've got 1/2 the mass, which is the combined mass of both of them, is 15 kilograms plus 9 kilograms, times their initial velocity, which is the 11.78 meters per second, plus my mu value, times their combined mass, which is the 15 plus 9 kilograms, times 9.8 times 8 meters. And I'm going to set that equal to 0. All right, if I do the algebra, I get that the coefficient of kinetic friction is going to be equal to 0.345. And it will not be negative because I should have added this. The direction of the force is to the left. It's against the direction of motion. So this force term is going to be negative. Excuse me, not that force term. The force of friction. Okay, and that makes the work term negative as well. So when I plug in these numbers to get the work, I should be getting, I can use the negative 9.8 here. All right, that's work and energy for a pretty complex system.